Hello, my name is Stefan Hougardy and I will talk on the approximation ratio of the two-opt heuristic for the Euclidean traveling salesman problem. And this is joint work with Ulrich Brodowsky. So in the Euclidean traveling salesman problem, we are given endpoints in the plane and want to find a shortest tour connecting all these points. This problem is well known to be NP-hard, so we are interested here in approximation algorithms. And for an approximation algorithm, we say that it has approximation ratio R if it always finds a solution that is at most R times as long as an optimum solution. And for the Euclidean traveling salesman problem, we have in some sense a best possible result for an NP-hard problem. Namely, we know that there exist polynomial time approximation schemes, which essentially means that we can find in polynomial time a solution that is arbitrarily close to an optimum solution. However, these results are mainly of theoretical interest. So we are interested in heuristics that we can use to solve large Euclidean traveling salesman problems in practice. And one such heuristic is the so-called two-opt heuristic that has been studied for more than 16 years now. And it is based on a very simple local operation, which is called a two-move. And in a two-move, we simply replace two edges of a tour by two other edges. So why should we do this? So the idea, of course, is we want to get a shorter tour. And so we call a two-move an improving two-move if indeed this operation yields a shorter tour. So here we see a simple example. So here we see a tour. And now we can choose, for example, these two green edges and remove these and replace them by these blue edges. And this way we got a shorter tour. And the idea of the two-opt heuristic now is we simply repeat this process as long as we can find improving two moves. So in this example, there will be another improving two move, namely we can choose these two green edges, remove them, replace them by the two blue edges, and then we have to stop because there's no further improving two move. So formally, we can state the two-opt heuristic as follows. So we start with an arbitrary tour for our point set V. And as long as we can find an improving two move, we will perform this two move. And if there's no longer a two move in an improving two move, we will output the current solution. And a tour where we cannot find an improving two move will be called two optimal. So this, of course, means that the output of the two-opt heuristic will always be two optimal. And another way to define this is that whenever we have two edges in our tour, then the length of these two edges is bounded by the length of the two edges by which we could replace them. So the question now is, what is the approximation ratio of the two-opt heuristic? And so it turns out in practice, two-opt heuristic yields quite good results. So for example, for random point sets, one usually finds a solution that is within 5% of the optimum. However, here we are interested in the worst case behavior. So the question is, what is the worst case approximation ratio that we can have if we apply the two-opt heuristic? And here, so far, only lower and upper bounds were known. Namely, we have a lower bound, which is essentially log n over log n, and an upper bound, which is log n times some constant. And so our result now says that we can close this gap. Namely, we can show that the approximation ratio of the two-opt heuristic for Euclidean TSP is log n over log n up to some constant factor. So how do we prove this result? So our proof consists of three main steps. In the first step, we reduce the problem to so-called crossing-free pairs of tours. In the second step, then, we reduce the problem to a problem in double-weighted arborescences. And in the third step, we show some weight bounds for double-weighted arborescences, which then will yield our result. So let's start with the first step. So the reduction to crossing free pairs of tours. So it's very well known that if we have a Euclidean TSP instance and if we have a two optimal tour, then we cannot have a crossing as we see here in this example. because if we have such a crossing, we will find an improving tour move and would get a shorter tour. So two optimal tour has no crossings, and so an optimal tour, as we see here, also has no crossings. But we want a much stronger result, namely, we want, if we look at an optimum tour, as we see here, and a two optimal tour, which is here the green tour, then there shouldn't be a crossing between the two tours. This is, of course, usually not the case. So in this example, we see that there are three crossings. But there's a simple way to get rid of these crossings. Namely, we can consider so-called subdivisions of a tour. And by this, we simply mean we add some more points on the lines of a tour. And by adding points on the lines of a tour, of course, we see that the tour is still optimal for the new point set. And it's also not difficult to see that the tour will still be too optimal if it was too optimal before. So adding some points preserves optimality and true optimality. And so this means if we replace all the crossings by new points, we will still have an optimum and a true optimal tour. And we didn't change the length of the tour. So if for the new instance, we can prove our approximation ratio, then this will also apply for the original instance. We have to be a bit careful because we may get a lot of crossings, but this is not a problem. So because in the worst case, we get a quadratic number of crossings, and because we want to prove a log n over log n factor, it doesn't matter whether we replace n by n squared. So this immediately shows that we may assume that our optimal tour and the two optimal tour do not cross. And this finishes already the first step. So in the second step, we want to reduce our problem to a problem in double-weighted arborescences. And so for this, we have a look at a slightly larger example. So here we have some points. We have an optimum tour. And here we have blue edges, which are the edges of a two optimal tour. And now we want to compare the length of the two optimal tour with the length of the optimal tour. And for this, we partition the edges of the two optimal tour into three sets by looking at the area enclosed by the polygon of the optimal tour. And we will denote by S1 all the edges that lie inside of the optimum tour polygon, by S2 all the edges in the exterior of the optimum tour polygon, and by S3 we will denote all the edges that are part of the optimal tour. And in the following, it will be useful to have some orientation for the two optimal tours, so let's fix some orientation. So how can we bounce the lengths of the edges in the sets S1, S2, and S3? So for X3, it's very simple because S3 is part of the optimum tour, so the edges are certainly bounded by the length of an optimum tour. So for S2, we will apply the same approach as we will do for S1. So let's concentrate on the set S1. So let's remove the edges in S2 and S3, and let's see how we can get a bound on the total length of all the edges in S1. And so for this, we partition the edge set S1 into two subsets, and we consider some fixed edge E0 with endpoints X0 and Y0, and partition all the edges in S1 with respect to having the same orientation as E0 or having opposite orientation to E0. And what do we mean by having the same orientation? So we can start going around the optimum tour, starting in the point X0, and now we go around the tour. And whenever we meet an edge of S1 for the first time, we distinguish whether we hit this edge at the head or at the tail. And if we hit the edge at the tail, we will put it into the set S1 prime. And if we hit the edge at the head, we put the edge into the set S1 double prime. And so in this example, all the edges that are green shaded are now the edges in S1 prime, and these are the edges that have, in this sense, the same orientation as this chosen edge E0. And now proving a length bound for the edges in S1 prime works the same way as for the edges in S1 double prime. So let's simply consider the set S1 prime. So how do we get a length bound now for these edges? So the idea is the edge set of the optimum tour and the edges in S1 prime form a planar graph. And so we can have a look at the planar dual. And so we take the planar dual, except that we do not take a vertex for the unbounded region. And then we get a tree, as it's easy to see. And we will orient the tree by orienting the dual edge to this edge E0 as the root edge of this arborescence. And this way we get a unique orientation and we get this green arborescence. And so on this arborescence, we now want to define two weight functions on the edges, namely a weight function C and a weight function W. And we will have a closer look how to define this by looking at some region of this planar graph. So here's one region of the planar graph. We have the vertex for the dual graph, and now we are interested to assign the C value and the W value to this green edge. And so the C value is very easy to define, namely the C value of this green edge is just the length of the corresponding dual edge. And for the weight function W, so we want to assign the weight W to this green edge. For this, we simply take all the edges belonging to the optimum tour, which are in our case here, all these red edges in the border of this area corresponding to the end point of this green edge. And so this is then the weight function W. And so why is it useful to have such a definition? So if we consider the total weight, so the total C weight of all the edges in our arborescence, this just corresponds to the total weight of the set S1 prime. So these are simply all the blue edges in our example. And the total weight W of this arborescence then corresponds to the total weight of all the red edges, which is the total weight of an optimum solution. Now, if we have these two weight functions, we can derive two inequalities. And the first inequality is what we call a combined triangle inequality, which simply arises if we look at an area in our planar graph and we have one such edge here, then the length of this edge is bounded by the length of all the other edges in the boundary of this region. And so this simply follows by applying the triangle inequality to the edges of the optimum tour and the two optimal tour, and then will result in this inequality. The second inequality that we get is what we called the combined two optimality condition. And for this now we consider two edges in the arborescence. We consider the corresponding dual edges, so these two blue dual edges. And now for these two edges, we can apply the two optimality condition, which tells us that these two blue edges are at most as long as the connections of their tails and their heads. And so these two connections we can bound in terms of edges on the boundary of this region that we see here. And this will yield then the second inequality, which is a combined two optimality condition. Now, if we have these two inequalities and these two weight functions on our arborescence, we can now go to the third step in our proof, where we derive weight bounds between the C value and the W value of our arborescence. And so the statement simply is, if we have two such weight functions and we know that the combined triangle inequality and the combined two optimality condition hold, then we can bound the total C weight of our arborescence by the total W weight of our arborescence times some log over log factor in the number of edges of this arborescence. and some constant factor. And since the C weight corresponds to the total weight of our set S1 prime, and W corresponds to the weight of the optimum tour, this is our desired result then. So it remains to prove this main lemma. So how do we prove this? So the idea is we partition the edges of our arborescence into so-called fast-growing and slowly growing edge weights. And edges with slowly growing edge weights turn out to be the good case, because all these edges together in total will have a small edge weight. And for the fast-growing edges, it is a bit more complicated to get a bound. And for these, we have to partition these edges into subsets of edges which have similar weight. And if we use this partition, then we can also get a bound on the total weight of the fast-growing edges. So let's have a look at this in a bit more detail. So what is the definition of a slowly growing edges? We want to call an edge slowly growing if its C weight is bounded by K times the maximum C weight that we see on the boundary of some face in our planar graph, or correspondingly on the outgoing edges in our arborescence. And these edges are called slowly growing. And we collect all these slowly growing edges in a set which we call E prime. So E prime contains all slowly growing edges. And then it's not too difficult to prove that we can bound the total C weight of these slowly growing edges by K over 2 times W of A. So that's the first bound that we get for the slowly growing edges. And we will later see, so this result holds for all values of K, and later we will see what is the right value for K that we should choose. Now for the fast growing edges, so these are the edges where the edge weight is by at least a factor of K larger than any other edge on the boundary, or in the dual graph incident to this vertex Y. And for these, it's a bit more complicated to get a bound. And we have to subdivide the set of fast-growing edges into these sets ER, where ER contains all the fast-growing edges which have a C value which lies between R and K over 4 times R. And for these edge sets, we can prove, if we assume the combined triangle inequality and the combined 2 optimality condition, that the total C value of such an edge set is bounded by twice the W value of our arborescence. And having these two results for the slowly growing and fast growing edge sets, we can prove our main lemma as follows. So our main lemma says that C of A divided by W of A is bounded by some log over log factor. And so let's call this ratio K. So we want to show that K is bounded by this log over log factor. So we have this definition E prime are the slowly growing edges, ER are the fast growing edges, which have a C value in this range. And now we want to define R values so that we can partition the whole set of fast growing edges. And so for this, we have to simply define some sequence Ri, which is a geometric sequence, namely 4 over K to the I times W of A. And we define these numbers for I values between 1 and K over 6. So this means with all the sets ERI, we do not cover all the fast growing edges. Some edges are uncovered, but the edges that are not covered by these sets are only edges which have a very small C value. And now with these definitions, we get the following inequality. So we know by definition, K times W of A is C of A. Now, what is C of A? So that's the total C value of all the edges in our arborescence. So these are either edges which are fast growing and that we collected in these sets ERI, or these are edges that are slowly growing, which are in the set E prime, or these are edges which are fast growing and have a small C value, which are not covered by our sets ERI. But here we know that their weight is at most 4 over k times to the k over 6 times W of A. And in the worst case, we have all edges having this small weight. So this is certainly an upper bound on the total C value of all these edges. And now we can plug in our two previous lemmas for the slowly growing and fast growing edges. And so we know that C of ERI is bounded by twice the W value. So this is the first bound that we plug in. For the set E prime, we had this bound K over 2 times W of A. And so the last term we simply keep the same. And now we see we can divide this inequality by W of A. And if we do so, what remains is an inequality involving only K and the number of edges in our arborescence. And then after some algebraic manipulation from this inequality, we get the desired result, namely that we can bound K by 12 times log over log log in the number of edges of our arborescence. So this proves the main lemma, and so the main lemma then implies that our set S1 prime is bounded by this log n over log log n factor times the length of an optimum tour. And so this then essentially yields our approximation ratio for the two-opt heuristic for the Euclidean traveling salesman problem. So here are some concluding remarks. So we have shown that the approximation ratio for the two-opt heuristic for Euclidean TSP is log n over log log n up to some constant factor. And the natural question is, what happens if instead of two-opt, where we allow two edges to be exchanged in each iteration, we allow what is called the k-opt, namely where we allow to exchange k edges. And in this case, our result immediately implies that also for the k-opt heuristic, we get a log n over log log n approximation ratio. And this is quite surprising because in many other cases, we know that the k-opt heuristic is strictly better than the two-opt heuristic if k is strictly larger than 2. But this is not the case for the Euclidean traveling salesman problem. Another possible extension is if instead of Euclidean traveling salesman instances, we consider the more general metric traveling salesman instances, so where just the triangle inequality holds. And so in this case, we can show that the two-opt heuristic has approximation ratio, which is exactly square root n over 2. Okay, so that's the end of my talk. Thanks for your attention.